So good afternoon, gentlemen. So it's my pleasure to introduce Hywel Normington from the Strathclyde University in Glasgow, who is going to talk about the Landau-Lifshitz-Gilbert equation, about a numerical solution to the application to magnet restriction. So Hywel is a PhD student of Michael Jerry, who was a student of the Pretorius in Vienna, the Technical University of Vienna, and then he moved to Glasgow, and now he is back in Italy, and he is part in Bologna. So
yeah.
I have to open here. Sorry.
No problem. Very good. Okay. Hi. So yeah, as mentioned by Martin, my name is Hywel Normington. I'm currently a PhD student at the University of Strathclyde. Michael Jerry, who some of you may know, is at the University of Bologna, which is in Italy, a lovely place. And yes, I'm going to be talking about the Landau-Lifshitz-Gilbert equation, specifically focusing on magnetorestriction or magnetoelastic effects. And we're going to be presenting this integratively design. So first of all, I'll go through some of the description of the physics, because without it, this is a pointless discussion. Afterwards, then we'll go through the algorithm we designed, talk about some of its features. Then we'll go through the numerical analysis, trying to show you that it's actually worth some salt, and also numerical experiments to try and convince you that my analysis is actually correct. So first for the physics, if we have some metallic body, usually you'd start with something like iron. If you apply magnetic fields to this metal, the dimensions of this object are going to change. So, for example, on this slide, we have this metallic block, and we've applied this field to it, and it's distorted a bit. This is extremely exaggerated. Typically, would not be anywhere near this level, but we want you to actually be able to see something. And so this will be measured by what we call the displacement, and we're going to be calling this U, and this is just some number in R cubed. And this specific effect, where you apply a magnetic field to your ferromagnetic body, is called magnetorestriction. On the other hand, you have inverse magnetorestrictive effect, and this is where you apply some force, you change the body, you deform it, and in turn, the internal magnetic state of the material is going to change. And the important thing to note here is that M, which is the magnetization, this vector is in S2. So this has constant unit length everywhere, because this is a quantum mechanical effect that we've known for a while, which is yeah, I'll get to that later. So when we have these materials, which we're going to call smart materials, you have a couple of kinds, but the ones we're focusing on are magnetorestrictive. And usually the effect of magnetorestriction is going to be very, very small. The material we use here is something called thecosib. I do not know the chemical name for this, so we're just going to call it that. The largest material, pure elements, will be cobalt. This has the most magnetorestriction. You can get up to 60 parts per million of extension. If you want anything more than that, you need these fancy materials such as terminal D, or even more fancy materials, MSMAs, which can have 6% changes in their dimensions, which is out of our analysis here. We can't touch these because we're going to stick to these small strain deformation case. So if we ignore for a moment any of this magnetoelastic behavior, the internal state of our material is simply described with micromagnetics. And here we have this magnetization vector, omega, which is up here. Sorry, magnetization vector M described on omega. And we described this using an energy functional, which was originally given by Brown in his book 1963-ish. There were some people before that, but Brown's the first pioneer of this work. And we described this with a couple of different effects. So the primary one for ferromagnetic materials is the exchange. And this is described vaguely by this picture here. Suppose we have two arrows, and these represent the magnetization vector. If you're close to each other, you'll want to point in the same direction. And this is how you get this long-range magnetic order. And this is vaguely shown in this picture up here. We have these arrows all pointing in the same direction here, and all pointing in the same direction in this location as well. And the way we describe this phenomenologically is with this term here, which is the gradient of m, and simply minimizing this energy means that we want to lower the amount of change we observe throughout the material. They all want to point in the same direction. The other terms we can take into account, such as anisotropy and external fields, these are described by this term here, which is just some positive term, and this describes how your magnetization interacts with your crystal lattice. Certain directions are going to be preferable to other ones. If you have a cube, typically it will be along the cubic axes. If you have something that's hexagonal, you'll have it across different axes. If you want to apply an external field to this, which is what we were mentioning earlier, where we apply a magnetic field and we get distortions, we can model this with an external field, and all this does is encourages your magnetization to point in the same direction. So here we apply a magnetic field, and then they all start trying to point in the same direction. Lastly, we have this term called the magnetostatic term, also called the demagnetizing field. And the essential description of this is that we're trying to make our magnetization understand Maxwell's equations. If we don't have this term, it will typically not behave quite like Maxwell's equations describe, unless you have certain cases of very small materials or specific shapes. In our work, we're going to completely ignore this because we don't actually care about it. We're not trying to get the most physically realistic system. All we care about is the interaction of this exchange term with the elastic behavior. If you want to make it a fancy calculation, you can include this, but you will end up spending hours and hours and hours of computation for this effect when you're not really interested in it anyway. So for macromagnetics, you have two cases. You have the static case, which you're simply minimizing your energy, subject to, again, this unit length constraint, where the norm of m should be 1. You also have your dynamics, and this is where the LLG equation, the Landau-Lifshitz-Gilbert equation, comes into play. It's described by the time derivative being equal to this cross product m with some other terms involving m. The interesting thing to note here is that if I take m dot dtm, because I have these cross products involving m, it's 0, which means that the time derivative of m and m are perpendicular. We described this using this HEFF, the effective field term, and it's essentially modeling how the magnetic field is on local behavior. Not strictly, this is not a real magnetic field, it's a pretend one, and this simply tells you which direction is going to lower your energy the most. To model the dissipation, we use this alpha term. So if you have alpha equals to 0, your system should not be losing any energy at all. If alpha is very large, you're essentially just back to doing statics again, and you should probably just ignore the dynamics. If we want to include this now, the elastic behavior, we throw away a couple of these other terms. So magnetostatics, as I mentioned, is gone. We'll ignore for a moment the anisotropy and also the external field. And we pick up this quadratic form. You'll probably recognize this one if you do small strain elastics, but instead of having epsilon u on its own, we've got an epsilon u minus an epsilon m. So this is going to be called the magnetostrain, and it's modeled with this theme here, which is a quadratic form again of m tensor m, which makes it very, very difficult to deal with and quite nonlinear. The tensor in front of it, this Z tensor, it's called the magnetostriction tensor, and this helps you describe the crystal class that your material belongs to. Typically, you'll just have an isotropic and isochoric material, which means you throw away all of your constants except for one. We have tried to avoid doing that simplification because it's not really necessary. We again have your usable symmetric total strain, which is just gradients of u. And the stress from Hooke's law is slightly different. Rather than being C epsilon u, you have C epsilon u minus epsilon m. As I mentioned, we've only got certain terms for the effective field, and this is simply the Laplacian, which comes from the Dirichlet energy up here, and also this much more complicated 2 times Z transpose times the stress multiplied by m. This is where most of your non-linearities come into play, and this is where the trouble begins. When you have your system, you need to pick your system of equations to actually model this. And we choose the conservation of momentum law and also the LLG, because this is our micromagnetic equation. And you can now see really where this coupling is going to come into play. So not only are we nonlinear, especially because of this term here and the effective field, we now have a coupling where the magnetization shows up in the conservation of momentum law, and also the displacement shows up in the LRG. The point of this algorithm is to try and rip this coupling apart and make it computable, and we go into that in a little bit. The only important condition that I've not mentioned so far is that U, our displacement, is going to be fixed on some boundary. If you really want to, you can input some different condition there, but it doesn't really matter. And this sigma n times equals G, ignore it. This is for finite difference people. We don't have to do any of that stuff. And same for this boundary term involving F. And again, we now need to take into account also the unit length constraint. So it should be as a 1 everywhere. And F is usually just going to be gravity, which means your material will be slightly pulled down. Gravity is typically extremely weak. If you rotate your magnet, nothing really happens, which is a good thing. And G will be some traction. If I take my magnet and I smack it with a hammer, it's probably not going to behave quite the same as it did a minute ago. If you hit it hard enough, obviously you're going to break your material, but the magnetization will have a small ripple. Talking more in depth about the LLG equation itself, we have nonlinearity, as I mentioned. You have non-unique solutions, which comes from this unit length constraint, because it's non-convex, and also your solutions that you get are going to be extremely low in regularity. Any discrete system that you build, this should have a couple of conditions. So first of all, you should try to preserve this unit length constraint here. The norm of M should be 1, otherwise you're not modeling LLG. And from that, you get this, again, m dot dtm equals 0. The energy law is where we're going to try and recover any of our lost regularity. And this simply says that the total energy, so the potential energy here, plus the kinetic energy, which comes from our material wiggling around, should be decreasing over time, described here by this, modulated by this alpha term here, belonging to the LLG equation. Typically, you will not have an equality here from any system that we design. You'll have an inequality. You have to weaken this slightly. And additionally, we're going to weaken this constraint here. So not having the norm of M be 1 everywhere will weaken this to be sufficiently close, provided your time step is sufficiently small. Now, just to try and get an idea of what LLG actually does, if I have no dissipation at all, my magnetization vector here will simply rotate around the effective field and it will never lose any energy. If I was to ignore the fact that it's precessing, I would just have this damping. My magnetization simply wants to rotate and join up with the effective field. And if we combine these, we get this spiraling behavior all the way into the effective field. Now, this happened locally, which means you're probably not going to get a uniform field at the end of this. You'll get something more interesting, especially if there's boundary conditions. But anyway, we'll move on now. So to the algorithm, we're going to rename the derivative term to be V, simply because it's going to be a free variable in a moment. And then we can rewrite LLG in this more compact form, where we've hidden all of the non-linearities into this term over here. So this is a fairly nice portion over here. This is linear now in V. This is simply just some functional eventually. And then this is full of all of our horribleness. If we now use the idea we had earlier, where m dot dtm is 0, we change it from being the time derivative to just some general function. We can test this and get rid of this term entirely. So this is now gone. The nonlinearity is gone. We have a natural linearization. And so these terms here with this perpendicularness, we will translate this into a discrete tangent space, and boom, we can now switch to using linear systems. We can have, we use first order finite elements because these are the simplest we can use. If we try and go any simpler to constant functions, the constraints on the unit length are going to be way too harsh. The discrete tangent space only holds at the nodes rather than holding everywhere, which is keep it like this. Given some approximation m, you can define this tangent space at every single one of the nodes, and then you can update from there. And as I mentioned earlier, we define now the free variable v.
Could you just collapse this picture of your submarine because it's maybe the most left one.
Is that good?
Yeah, maybe
In
the
the top
most
left corner of the picture, there's the minimize button.
Ah, that's a good question. There we go.
No.
Now we can actually read my stuff.
Yeah, wonderful.
Okay, so when we use this tangent space at one node, it looks roughly like this. You have some magnetization, and then we define this tangent space to be everything perpendicular to it. We're going to be looking for VHI, which is this discrete time derivative in this space here. Because we have this Dirichlet condition for the displacement, we simply do this the most easy way possible. We just intercept this with H1D, enforcing explicitly that it's equal to 0 in the parts that it's 0. Now, suppose we've calculated already, which we're going to get to in a minute, how to do that, the time derivative. How do you actually update from one time step to the next? Keep in mind, we want to use unit length. The simplest approach would be to just take your finite element approximation, add on the update term, and then divide by the size of it. Now it's going to have unit length anyway. That would be nice, but this is definitely not going to be in the finite element space, so this would be pointless. The nodal projection of pi h offers a different approach. Rather than doing this normalization everywhere, you simply do it at each node. And this is good. Now we have the norm of 1 being equal to 1 everywhere, so the norm of m being equal to 1 everywhere. But the problem is, this is no longer going to be unconditionally convergent. We'll have conditions. The conditioning of that is really horrible. We have weakly acute meshes now being required. In 2D, very simple. All of your standard mesh builders will build weakly acute meshes. If you try to move to 3D, good luck. You can start with a weakly acute mesh and then trying to refine it further into another weakly acute mesh is difficult in itself. If you don't have one to begin with, you're practically screwed. So instead, we're going to switch to ignoring entirely this normalization step. We're going to do projection free. And this is good enough. It's no longer going to be size 1 anywhere, probably. However, it will be sufficiently close. And we can measure this precisely with something proportional to the time step. If you make your time step very small, you can make it as close as you want. Now, just to try and get an idea of what this projection-free method actually does, we begin with an approximation n, and this happily lies on the sphere. We then search for an update v, and then scale it appropriately. And then we add them together, and now we can see we're no longer on the sphere, which is, we think a bad thing, but as I mentioned, we have this unit length constraint error term, which we can show is sufficiently small. And so as we continue doing this, m will slowly get away from the sphere, and we need to control this. So simply set your time step to be very small, and then mi plus 3 will be very, very close to where mi was. Now, onto the actual algorithm itself. Onto the actual algorithm itself, we have this formulation. This is essentially what I wrote earlier, the linearized form, where we have tested everything with these discrete functions. The subscript h here on the inner product doesn't mean anything interesting. It just means we're doing a less precise integration. And on the right-hand side, we have an implicit integration for this Laplace term. This beta parameter becomes very important later on. And inside the magnetostrain, which I've labeled like this, we've got the displacement, which we haven't touched. And then the projection operator has been applied to the current approximation of it. Now, you may say, okay, this is no longer nodally projection free because I'm using one, but that's not the point, because in step 2, we do not use a projection. And we are safe to use non-weakly acute meshes, provided projections only happen when there are no gradients involved. So if I did it every step, I would have a projection at this step, and that's then requiring weakly acute meshes. And so the displacement formulation is not very interesting. Again, we have this projection again, which is just a discrete version of the conservation momentum law. And the important thing to note here is that in step 1, every term has an I, but in step 3, every term has an I plus 1. And this is what we mean by decoupled. So now I can solve my first equation entirely in one step, then make an update to the next step, and afterwards I'm now solving this different equation. If you didn't do this decoupling, I'd have to solve some much more complicated system involving all of these terms at the same time. But this means I can decouple it, I can solve 2 linear systems, and it's actually quite easy to implement this computationally. I'm the one who wrote the current implementation, so don't look at the code, please, it's quite terrible, but it is actually easy if you know what you're doing. The additional feature is we don't need these weakly repeat meshes anymore. You can use any old mesh generator, so we use NetGen, which is entirely free and builds reasonably good meshes. And we've also included these body forces, so F, gravity, and traction. And we have a much more interesting tensor describing the magnetorestriction. When we move on to the stability and well-posedness, we have no conditions. If we were using these projections, yes, you would require instead conditions on the mesh. And as I mentioned, this theta term needs to be strictly between, it needs to be specially cared for. It needs to be between 1/2, not including it, or 1. So if you try and go to 1/2, this estimate down here means we will lose control over the grad theta. This would be good if you were trying to do something in the spirit of Frank-Nicolson, good for energy conservation laws, but bad for our analysis. And so this term, we require it to be strictly positive just so we can get away with estimating this term. Now, back to this energy law, which is the pesky part of our problem. This is what the continuous energy law looks like. So given some time t, if you add on the current kinetic energy and the actual energy, you should have less energy than you started with. That's at least the hope. And if you have more dissipation, it should lose it quicker. The discrete energy law, which is trying to mimic the continuous one of the actual continuous system, is very similar. So we have the final time and the final time here. These are essentially the same term. The dissipation term is also essentially the same, just with a discrete sum. And again, the final term, it's all the same. The difference here is that we have an equality, which is a good thing. The bad thing is that we have this error term and also this strictly positive implicit error term. You can simply throw this term away and then you get inequality. So this one causes no trouble, but the error term, to show that this goes to 0 sufficiently fast, is problematic. And I'll get to that in a moment. So we can prove that the decoupling hasn't actually affected the system. We can get back to the coupled system simply by lowering the discretization parameters. So send H and K to 0. The problem is, if you want the continuous energy law back, you're going to have to satisfy this very nasty CFL condition, which is that the time step should scale like H to the 9, which is completely ridiculous. However, this problem appears to be part of our analysis. It's not something we actually notice in any numerical experiments. Okay, now, because the energy law needs to be respected, we can do some experiments just to check whether or not that coupling is actually coming into play. And we can test this by just changing theta to see how much we need to take into account. So if we start with what I'm calling a hot magnet, even though the temperature is, strictly speaking, 0 Kelvin, which means it's very, very random, so you have lots of energy to begin with. You get this quite large energy at 475, and then it decreases as expected, without using any special parameters, without having to take into account the coupling of K equals H to the 9. The problem is that theta needs to be very, very close to 1/2. If I have theta being 1, this energy reaches down to 469, when for theta equals 1/2, well, close to 1/2, it's about 473. You do not want to be just dumping energy from your system for no reason, because it's not physical. And so if you're doing this implicit approach, theta should be 1/2 plus some epsilon. And as I mentioned, your LLG system is completely useless if you can't get back to the unit length constraint. And this constraint here shows that it should scale linearly with K. And this is exactly what you see in this very boring straight line graph. The more interesting measure of error would be this an infinity norm. So what's the maximum size of M? Well, you can see that it behaves, well, it's not linear at all. We don't have any theoretical control over it. You can get some if you use a CFL condition, but we want to try and avoid those as much as we can. And so we'll just now finish up with the conclusion. We've got a decoupled, unconditionally convergent, excluding one portion of the energy law, and the integrator is linear, and we include magnetic friction. We don't require these weakly acute meshes, and we can enforce the energy law with a bad CFL condition. However, previous methods didn't even bother looking into the energy law at all. They simply said the energy was bounded, and they were happy with that. So despite the CFL condition being quite negative, it's still an improvement on the literature. Now, in future, what do we want to do? Well, there's a reason why I'm here in Prague, to try and talk to Martin about most of these ideas. We've got, first of all, an extension to non-simple materials, which are materials that can depend on the gradient of the deformation gradients. Then you also have finite strain magnetoelastics. This is more difficult because your reference frame changes, and the magnetization then becomes dependent upon where the material has moved to, because the magnetization doesn't care where it started, it needs to know where it is at the end. And so you now have a problem where you don't know what your deformation is, and also your magnetization depends on where it's deformed to as well. This is a much more complicated energy expression where you have W's, which are your function, describing energy, and depending on the gradient of Y, which is the deformation, and then M takes into account where Y is. So it needs to know where it's deformed to. And then when we integrate over this exchange energy again, we need to integrate over the final outputs deformation. And again, we have this magnetostatic term, but this is already over R cubed, so it's not too big of a deal. Okay, right, thanks for listening. I think that was a bit quick.